Hello, dear wanderer. Welcome back to the Midnight Explorer. Tonight, I want you to find somewhere comfortable, somewhere soft. Maybe it's your bed with pillows propped just right. Maybe it's a chair by a window where you can see the stars. Wherever you are, let yourself settle in. Take a breath, a deep one. Hold it, and release. Good. Tonight, we're going on a journey. Not across continents or through forests, but outward. Far, far outward. Beyond the clouds, beyond the moon, beyond our sun and its family of planets. Tonight, we're traveling to the islands in the cosmic ocean. Tonight, we're exploring galaxies. But this isn't just a story about space. It's a story about us, about how we came to understand our place in something so vast, it makes our minds ache. It's about the dreamers who looked up and refused to look away. The mathematicians who saw patterns in the dark. The photographers who captured light that had been traveling for millions of years just to reach their cameras. So close your eyes if you'd like, or keep them open, gazing at nothing in particular. Let my words paint pictures in your mind. And let's begin where all good stories begin, with a question that changed everything. It is a clear night in the year 964 AD. In the deserts of Persia, an astronomer named Abd al-Rahman al-Sufi sits beneath a sky so dark and so clear that the heavens seem to press down upon the earth. He has been studying the stars for decades, cataloging them, measuring their brightness, mapping their positions with an accuracy that will not be surpassed for centuries. But tonight, something catches his eye. Something that shouldn't be there. In the constellation of Andromeda, there is a small, faint smudge of light. It doesn't twinkle like a star. It doesn't move like a planet. It simply exists. A little cloud, he calls it. A nebulous star. He carefully notes its position in his book, The Book of Fixed Stars, never knowing that he has just become the first human being in recorded history to document a galaxy beyond our own. Can you imagine that moment? The pen in his hand, the parchment before him, the cool desert air on his skin. The absolute solitude of discovery. He didn't know what it was. How could he? The very concept of a galaxy, separate islands of stars, each containing hundreds of billions of suns, was an idea that wouldn't crystallize for another 900 years. But he saw it. He marked it. He preserved it for future eyes. This is where our story truly begins. With curiosity. With the simple act of paying attention. With someone looking at the same sky humans had looked at for thousands of years and seeing something new. Or perhaps seeing something that had always been there, but truly seeing it for the first time. Let's linger here for a moment. Let's understand what the sky meant to people in al-Sufi's time. The year is 964, and the world is a tapestry of civilizations, each looking upward, each constructing their own understanding of the heavens. In Baghdad, scholars gather in the House of Wisdom, translating ancient Greek texts and pushing the boundaries of mathematics and astronomy. In China, astronomers meticulously record comets and novae in imperial records that stretch back thousands of years. In Europe, monks copy manuscripts by candlelight in stone monasteries, preserving what knowledge survived the fall of Rome. The sky is not just a curiosity. It is a calendar, a compass, a clock. It tells farmers when to plant. It guides sailors across featureless oceans. It marks the passage of seasons and the approach of festivals. The sky is woven into the fabric of survival itself. But it is also something more. It is mystery. It is the dwelling place of gods and the destination of souls. It is the great unanswerable question hanging above every human head. What are those points of light? Why do they move the way they do? What lies beyond them? Al-Sufi doesn't know that his little cloud is a galaxy called Andromeda, our nearest major galactic neighbor. He doesn't know that it contains roughly 1 trillion stars. He doesn't know that it's hurtling toward our own Milky Way at about 110 kilometers per second, and that in about 4 billion years, the two will collide in a slow-motion cosmic dance that will reshape both into something new. He simply sees, and notes, and wonders. This is the first gift galaxies give us: wonder. Now, let's jump forward. Not in space, but in time. 7.5 centuries pass in the blink of an eye. It is now the year 1610, and in Padua, Italy, a mathematician named Galileo Galilei points a new invention toward the sky: a telescope. It's a simple thing, this telescope. Just a few pieces of curved glass held in a leather tube. But when Galileo looks through it at the band of pale light stretching across the night sky, the band the Romans called the Via Lactea, the Milky Way, he sees something astonishing. It's made of stars. Thousands upon thousands of individual stars, too faint for the naked eye to separate, but there they are, revealed by the magnification of the telescope. The Milky Way isn't milk spilled across heaven. It's not a road made of light. It's stars, an unfathomable multitude of them. Imagine his heart in that moment, the catch in his breath, the way his hand might have trembled as he adjusted the focus. Here was proof that the universe was far larger, far more complex than anyone had imagined. Every fuzzy patch in the sky might be hiding countless stars. Every dim glow might be a vast congregation of suns. But Galileo still doesn't know about galaxies. He thinks he's looking at the structure of the universe singular. He doesn't yet know that the Milky Way is just one galaxy among billions. That the universe is not a room, but a mansion with countless rooms. That we live in just one corner of one of them. Still, he has taken a crucial step. He has shown that magnification reveals hidden worlds. He has demonstrated that our eyes, miraculous as they are, can deceive us about the true nature of reality. He has proven that tools can extend our senses into realms we could never access alone. The telescope becomes humanity's new eye, seeing deeper into the night than we ever thought possible. Another century passes. It is now 1755, and in Prussia, in Königsberg, a young philosopher named Immanuel Kant is thinking dangerous thoughts. Kant has been reading about the Milky Way. He's been thinking about those fuzzy patches of light that astronomers call nebulae. Some of them might not be clouds of glowing gas within our universe. They might be other Milky Ways, other island universes. Each one a vast collection of stars separated from our own by immense gulfs of empty space. It's just a theory, a philosophical speculation. Kant has no telescope, no observations to back this up, but he has intuition. He has the ability to think at vast scales, and he has the courage to imagine that the universe might be far stranger and larger than anyone had dared to conceive. Let us move forward again, this time to the year 1845. In Ireland, William Parsons, the 3rd Earl of Rosse, has just completed construction of the largest telescope in the world. It's a monster, a 6-foot diameter mirror housed in a tube that's 54 feet long. They call it the Leviathan of Parsonstown. It's spring, and the weather is clear. Parsons points his great telescope at a nebula catalogued by Messier as M51. And there, in the eyepiece, he sees something that takes his breath away. It's a spiral, a perfect spiral, like water going down a drain or a nautilus shell, or a pinwheel spinning in slow motion. The nebula has structure, delicate arms reaching outward from a bright central core. It's the first time anyone has seen a spiral galaxy clearly enough to understand its shape. Parsons draws what he sees. His sketch will be reproduced in journals and books around the world. The Whirlpool Nebula, they start calling it. But what is it? Is it a solar system being born with planets forming in that spiral? Or is it something far larger? The question deepens. Now, I want you to imagine something. I want you to imagine you're standing outside on a clear, moonless night. You're far from any city, far from any lights. The Milky Way arches overhead, that river of light flowing from horizon to horizon. It's beautiful. It's humbling. Now, imagine that someone tells you everything you can see, every star, every cluster, every wisp of light, it's all part of one galaxy. And there are billions more galaxies out there beyond what your eyes can perceive, each one containing billions of stars. How would that feel? Would it make you feel small, insignificant? Or would it fill you with a strange sense of connection, knowing that you are part of something so immense? This is the gift galaxies will ultimately give humanity. But first, we have to prove they exist. The 19th century marches forward. Photography is invented, and suddenly astronomers can capture light over time, recording faint objects that are invisible to the eye. Spectroscopy is developed, allowing scientists to analyze the light from stars and nebulae, breaking it into rainbows that reveal the chemical composition and motion of distant objects. The tools are getting better, the questions are getting sharper. And then comes a man who will change everything, Edwin Hubble. But before we meet Hubble, we need to understand the world he inherited. We need to understand what astronomers thought they knew about the universe in the early 20th century. It's 1900. The Victorian age is ending. Electricity is spreading through cities. Automobiles are beginning to replace horses. The world is accelerating, modernizing, reshaping itself. And in astronomy, there's a debate raging, a big one. On one side are astronomers who believe the Milky Way is the universe. Everything exists within it. Those spiral nebulae, they're probably just clouds of gas within our galaxy, possibly places where new stars are forming. On the other side are astronomers who believe in Kant's island universes. They think the spiral nebulae are separate galaxies, incredibly distant, each one comparable in size to our own Milky Way. The problem is, nobody can prove it either way. The nebulae are too faint, too distant. Even the largest telescopes can't resolve individual stars within them. All anyone can see are fuzzy spirals and ovals of light. Arguments are made. Papers are written. Astronomers pick sides. But the evidence remains frustratingly ambiguous. And then, in 1920, something extraordinary happens. Two astronomers, Harlow Shapley and Heber Curtis, stage a public debate at the National Academy of Sciences in Washington, D.C. The topic: the scale of the universe. Shapley argues that the Milky Way is enormous, maybe 300,000 light-years across, and that it contains everything. The spiral nebulae are inside it. Curtis argues that the Milky Way is smaller, perhaps 30,000 light-years across, and that the spiral nebulae are separate galaxies, island universes, millions of light-years away. The problem: both men present evidence. Both make compelling arguments. And at the end of the debate, the audience is no closer to an answer than they were before. The universe holds its secrets close. But now, finally, we come to Edwin Hubble. It's 1923, and Hubble has access to the most powerful telescope on Earth, the 100-inch Hooker telescope on Mount Wilson in California. Night after night, he photographs the Andromeda Nebula, capturing long exposures on glass photographic plates. He's looking for something specific: Cepheid variables. These are stars that pulse in brightness with a regular rhythm, and, crucially, there's a direct relationship between how fast they pulse and how bright they actually are. If you can measure a Cepheid's pulse rate, you can calculate its true brightness. And if you know its true brightness and can see how bright it appears to be from Earth, you can calculate its distance. It's a cosmic yardstick, and Hubble is about to use it to measure something extraordinary. One October night, he photographs Andromeda, and examining the plate later, finds something remarkable: a star that seems to vary in brightness. He marks it with VAR on the plate, the exclamation point betraying his excitement. He photographs Andromeda again and again over the following months, carefully measuring this variable star. He determines its period of pulsation. He runs the calculations, and the answer that comes back is staggering. The Andromeda Nebula is approximately 900,000 light-years away. Later measurements will revise this to about 2.5 million light-years, but even his initial estimate is revolutionary. It's far, far outside our galaxy. It is another galaxy, an island universe, just as Kant had imagined. Hubble has settled the debate. The universe is immensely larger than anyone thought. The Milky Way is not alone. We are part of a cosmos populated by countless galaxies, each one a vast congregation of stars. Can you imagine receiving this news? If you were alive in 1924 when Hubble's findings were published, how would it change your view of reality? Yesterday, the universe was one galaxy. Today, it's billions of them. It's as if you thought you lived alone in a house, and then discovered that the house is just one house of countless houses stretching to the horizon in every direction. And each house is full of people you never knew existed. The universe has suddenly become a much less lonely place and a much more mysterious one. Hubble doesn't stop there. He begins measuring distances to other galaxies. He classifies them by shape, spirals, ellipticals, irregulars. He creates a taxonomy of galactic forms, a kind of field guide to the universe. And then, working with a colleague named Milton Humason, he makes another discovery, one that's even more profound. They begin analyzing the spectra of light from distant galaxies, and they notice something strange. The light is shifted toward the red end of the spectrum. This is called redshift, and it indicates that the galaxies are moving away from us. The farther away a galaxy is, the faster it's receding. The universe, Hubble realizes, is expanding. Think about that. Really think about it. Every galaxy is moving away from every other galaxy. Space itself is stretching, carrying the galaxies along with it, like raisins in an expanding loaf of bread. This means the universe had a beginning. If you run the clock.
Let's pause now in our historical journey. Let's take a moment to understand what a galaxy actually is, not just as an abstract concept, but as a real physical thing, a place, a collection of matter and energy bound together by gravity and time. Close your eyes for a moment. Picture our own galaxy, the Milky Way. It's a spiral galaxy, shaped like a disk with a bulge in the center. If you could see it from above, it would look like a pinwheel with several elegant arms curving outward from the core. From the side, it would appear flat, like two fried eggs placed back to back. The disk is about 100,000 light-years across. A light-year is the distance light travels in 1 year, roughly 6 trillion miles. So we're talking about 600,000 trillion miles from one edge of the galaxy to the other. It's a distance that breaks our everyday intuitions about space. It's so large that even light, the fastest thing in the universe, takes 100,000 years to cross it. Now, within this disk are approximately 200 to 400 billion stars. Each one is a sun, many of them larger than our own. And around many of these stars orbit planets. Billions upon billions of planets. Rocky ones, gaseous ones, ones made of ice, ones bathed in radiation, ones shrouded in eternal storms. Between the stars is not empty space, but thinly scattered gas and dust, mostly hydrogen, the simplest element, but also heavier elements forged in the cores of ancient stars and scattered into space when those stars died. This interstellar medium is the raw material from which new stars are born. And threading through everything, invisible but undeniable, is dark matter. We can't see it, can't touch it, can't even directly detect it with our instruments, but we know it's there because of its gravitational effects. Stars orbit the galactic center too fast for the visible matter alone to hold them in place. There must be something else, something dark and mysterious, providing additional gravity. Dark matter makes up perhaps 85% of the galaxy's mass, yet we understand almost nothing about what it is. At the very heart of the Milky Way, buried behind clouds of gas and dust that make it invisible to optical telescopes, lies a supermassive black hole. We call it Sagittarius A star,
pronounced Sagittarius A, asterisk. It contains about 4 million times the mass of our Sun, all compressed into a region smaller than Mercury's orbit. This black hole is not just sitting there. Stars orbit it, whipping around at incredible speeds, completing orbits that take years or decades rather than the centuries or millennia you might expect. We've tracked some of these stars, watched them swing around the invisible gravitational anchor at the galaxy's core, their motion proving beyond doubt that something immensely massive lurks there in the dark. Now, let's zoom out. Let's pull back from the Milky Way and see it in context. Our galaxy has companions. The largest are the Magellanic Clouds, 2 irregular dwarf galaxies visible from the southern hemisphere. They're like moons orbiting a planet, smaller galaxies caught in the Milky Way's gravitational embrace. They orbit us, and eventually, over billions of years, they may be absorbed into the Milky Way, their stars becoming our stars, their gas fueling new generations of starbirth in our spiral arms. And then there's Andromeda, cataloged as M31, the galaxy that Al-Sufi saw and Hubble measured. It's a spiral galaxy larger than our own, containing perhaps 1 trillion stars compared to our few 100 billion. It's 2.5 million light years away, but it's not staying there. It's approaching us. I mentioned this earlier, but let's linger on it now. The Andromeda Galaxy is falling toward the Milky Way at about 110 kilometers per second, roughly 250,000 miles per hour. In about 4 billion years, the 2 galaxies will collide. But collide is a strange word for what will actually happen. Galaxies are mostly empty space. The stars are so far apart that when 2 galaxies merge, individual stars almost never actually hit each other. Instead, the 2 galaxies will pass through each other like ghosts, their gravity causing their structures to distort and tangle. Over hundreds of millions of years, the 2 spiral galaxies will blend together, their spiral arms disrupted, their stars scattered into new orbits. Eventually, they'll settle into a single large elliptical galaxy. Astronomers have already given it a name, Milky Way. Our Sun, if it still exists, and it will, the Sun has about 5 billion years of life left, will be thrown into a new orbit, possibly far from the galactic center, possibly closer. The night sky visible from Earth, or whatever rocky planet remains after our Sun swells into a red giant and then collapses into a white dwarf, will be utterly transformed. The Milky Way band we see today will be gone, replaced by a nearly featureless elliptical glow. But this is all in the distant future. For now, the Milky Way and Andromeda are separate, each spinning in the cosmic dark, each containing countless worlds where, perhaps, other beings look up at their own night skies and wonder about the fuzzy patches of light they see. Let's talk about the different types of galaxies, because just as there are different types of trees in a forest or different types of houses in a city, there are different types of galaxies in the universe. Edwin Hubble, when he classified galaxies, created a system that astronomers still use today. It's called the Hubble sequence, or sometimes, affectionately, the tuning fork diagram because of its shape. On one side are the elliptical galaxies. These are smooth, featureless balls or ovals of stars. They range from nearly spherical to highly elongated. They're labeled E0, almost perfectly round, through E7, very stretched out. Elliptical galaxies contain mostly old, red stars. They have little gas or dust left, which means they're not forming many new stars. They're like retirement communities for stars, places where the residents are old and the neighborhoods are quiet. Elliptical galaxies tend to form when spiral galaxies merge. The collision disrupts the orderly spiral structure, and the stars settle into random orbits, creating a smooth ellipsoidal shape. They're common in dense galaxy clusters where collisions are frequent.
On the other side of Hubble's diagram are the spiral galaxies. These are the ones that look like pinwheels or hurricanes when viewed face-on. They have a central bulge surrounded by a flat disk with spiral arms. The arms are regions where stars are actively forming, glowing blue with the light of young, hot stars. Spiral galaxies are further divided into ordinary spirals and barred spirals. Ordinary spirals have arms that emerge from the central bulge. Barred spirals, like our Milky Way, have a bar-shaped structure across the center, with the spiral arms extending from the ends of the bar. Why do spiral galaxies have arms? It's not because the galaxy is spinning like a solid wheel. If that were the case, the arms would wrap tighter and tighter over billions of years until the galaxy looked like a spiral staircase viewed from above. Instead, spiral arms are density waves, regions where stars and gas bunch up temporarily as they orbit the galactic center. It's like a traffic jam on a highway. The cars, stars, move through the jam, but the jam itself, the spiral arm, persists. Then there are lenticular galaxies, which are sort of in between spirals and ellipticals. They have a disk and a bulge like spirals, but no spiral arms. They've used up most of their gas, so they're not forming many new stars. They're transitional forms, perhaps spirals that are running out of fuel, or ellipticals that haven't quite forgotten they used to be spirals. Finally, there are irregular galaxies. These don't fit into the neat categories above. They're chaotic, lumpy, with no clear structure. Many irregular galaxies are small, like the Magellanic Clouds. Often, they're the result of gravitational interactions, galaxies that have been stretched and distorted by close encounters with larger neighbors. And then, as astronomers have probed deeper into space with more powerful telescopes, they've found even stranger things. Ring galaxies, which look like cosmic hoops floating in space. Peculiar galaxies, with tails or bridges of stars connecting them to neighbors. Galaxies with multiple nuclei, suggesting recent mergers. Galaxies that are colliding right now, frozen in the act by their great distance and the slowness of light. Each shape tells a story. Each form is a chapter in the history of that galaxy. And when we look at thousands of galaxies, we begin to see patterns, to understand how galaxies form, evolve, and die. Let's talk about what happens inside a galaxy. Because galaxies aren't just static collections of stars, they're dynamic systems where matter cycles from one form to another in a grand cosmic ecology. Stars are born in molecular clouds, vast, cold regions of gas and dust that can stretch for hundreds of light years. Gravity causes these clouds to collapse, pulling material together. As the cloud collapses, it fragments, and each fragment becomes a new star. The star forms with a disk of leftover material around it. From this disk, planets may coalesce. The star ignites, beginning to fuse hydrogen into helium in its core, releasing energy that makes it shine. For millions or billions of years, the star burns steadily, but eventually it runs out of fuel. If the star is small, like our Sun, it swells into a red giant, puffing off its outer layers into space. These layers form a beautiful planetary nebula, a glowing shell of gas lit up by the hot core of the dying star. Eventually, the core cools and becomes a white dwarf, a dense ember slowly fading over billions of years. If the star is large, more than about 8 times the mass of the Sun, its death is far more dramatic. When it runs out of fuel, it can no longer support itself against gravity. The core collapses in a fraction of a second, triggering a supernova explosion. For a brief time, the dying star outshines an entire galaxy. The explosion hurls most of the star's material into space at speeds of thousands of kilometers per second. What's left behind might be a neutron star, a ball of incredibly dense matter only about 20 kilometers across, but containing more mass than our Sun, or, if the original star was massive enough, a black hole. But here's the beautiful part. The material expelled by dying stars doesn't just vanish. It becomes part of the interstellar medium.
It mixes with the clouds of gas that will form the next generation of stars. And because dying stars create heavy elements in their cores, carbon, oxygen, nitrogen, iron, gold, the new stars that form are enriched with these elements. Our Sun is a third-generation star, made partly from the ashes of stars that died billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged in the cores of ancient stars and scattered into space when those stars died. We are quite literally made of stardust. Galactic recycling has given us existence. Now, let's talk about something strange, something that changed our understanding of galaxies forever. In the 1960s and 70s, astronomers began measuring how fast stars orbit in galaxies. They expected to find that stars farther from the galactic center would orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. That's what Newton's laws of gravity predict. But that's not what they found. Instead, they discovered that stars far from the galactic center were orbiting just as fast as stars closer in. In some cases, the orbital speed stayed constant all the way to the edge of the visible galaxy. This was impossible. The visible matter in the galaxy, the stars and gas we could see, didn't have enough mass to keep those outer stars in orbit at such high speeds. By all rights, those stars should be flung out into intergalactic space like stones from a sling. The only explanation was that there must be additional mass in the galaxy, mass we couldn't see, dark matter. Astronomers estimate that dark matter makes up about 85% of the total matter in the universe. It doesn't emit light, it doesn't absorb light, it doesn't interact with ordinary matter except through gravity. We know it's there because of how it affects things we can see, but we have no idea what it actually is. Is it exotic particles that barely interact with normal matter? Is it primordial black holes left over from the early universe? Is it something even stranger than we haven't thought of yet? We don't know. And that not knowing is thrilling. It means the universe still has secrets. It means there are still fundamental mysteries waiting to be solved. Dark matter forms vast halos around galaxies, extending far beyond the visible edges. These halos provide the gravitational scaffolding on which galaxies are built. Without dark matter, galaxies as we know them couldn't exist. The visible matter would never have clumped together tightly enough to form stars. In a very real sense, dark matter is the hidden architecture of the universe. We live in its shadow, shaped by its influence, and we've only just begun to glimpse its presence.
Let me tell you about a photograph. Perhaps the most important photograph ever taken. It's December 1995, and astronomers have a bold idea. They want to point the Hubble Space Telescope, the most powerful optical telescope ever placed in orbit, at a seemingly empty patch of sky, not at a bright star or a known galaxy, but at a tiny region near the Big Dipper where nothing of interest appears to exist. The region is so small that it's equivalent to looking at the sky through a drinking straw, or holding a grain of sand at arm's length. To the naked eye, there's nothing there, just blackness. But the astronomers want to take a long exposure, a very long exposure. They plan to point Hubble at this empty patch and collect light for days, allowing the faint glow of distant objects to accumulate on the camera's detector. It's a gamble. They're using precious telescope time that other astronomers wanted for studying known objects. If the patch of sky really is empty, they'll have wasted hundreds of orbits of the most expensive telescope ever built. But they believe. They believe that the universe is full of galaxies, that there's no such thing as truly empty space when you look deep enough. And so, over the course of 10 days between December 18 and 28, 1995, Hubble stares at this patch of darkness. The telescope takes 342 separate exposures, each one capturing photons that have been traveling through space for billions of years. The exposures are combined, layered like sheets of translucent paper, building up an image from whispers of ancient light. When the final image is revealed, the astronomers are stunned. The patch isn't empty. Far from it.
It contains approximately 3,000 galaxies. Spirals, ellipticals, irregulars, galaxies of every type and color, scattered across the frame like jewels on black velvet. And these aren't nearby galaxies. Many of them are so distant that their light has been traveling toward us for more than 10 billion years. We're seeing them as they were when the universe was young, when many of the stars we see in our own night sky hadn't even been born yet. This image becomes known as the Hubble Deep Field, and it revolutionizes our understanding of the universe. If this tiny patch of seemingly empty sky contains 3,000 galaxies, what does that tell us about the entire sky? Astronomers do the math. The whole sky is about 12.7 million times larger than the deep field. If galaxy density is roughly constant, that means there are approximately 100 to 200 billion galaxies in the observable universe. Let that sink in. 100 billion galaxies, each one containing hundreds of billions of stars, each star potentially orbited by planets. The numbers become so large they lose meaning. They become poetry instead of mathematics. But more than the numbers, the deep field shows us something profound about time. You see, when we look at distant galaxies, we're not seeing them as they are now. We're seeing them as they were. Light travels fast, about 186,000 miles per second, but the universe is so vast that light from distant objects takes eons to reach us. When you look at the Andromeda Galaxy, you're seeing it as it was 2.5 million years ago. The light now entering your eye left Andromeda when our ancestors were just learning to walk upright on the African savanna. When you look at galaxies in the Hubble Deep Field, some of them billions of light years away, you're seeing them as they were billions of years ago. You're looking backward in time. The universe is not just a place, it's a time machine. Every direction you look is a different era. The farther you look, the younger the universe becomes. And here's something even more miraculous. Those distant galaxies in the deep field, they look different from nearby galaxies. Many of them are smaller, more irregular. They're actively colliding with each other, merging together. Star formation is happening at a furious rate, making them glow bright blue. We're watching cosmic evolution in action. We're seeing galaxies when they were young and wild before they settled into the mature spirals and ellipticals we see in our local universe. We're witnessing the universe growing up. The Hubble Deep Field is followed by even deeper images. The Hubble Ultra Deep Field in 2004 stares at an even smaller patch of sky for even longer, revealing nearly 10,000 galaxies, some dating back to just 800 million years after the Big Bang. The Hubble Extreme Deep Field pushes even further. And in 2022, the James Webb Space Telescope, Hubble's successor, produces its own deep field. Because Webb observes an infrared light with longer wavelengths than our eyes can see, it can peer even farther back in time, seeing galaxies that are too redshifted for Hubble to detect. Webb reveals galaxies that existed just 200 to 300 million years after the Big Bang, when the first stars were igniting and the universe was emerging from its dark age. These images are humbling. They remind us that our existence is a fleeting moment in a story that spans billions of years. But they're also exhilarating. They show us that we have the tools and the ingenuity to see across vast gulfs of space and time. We can witness the birth of the universe itself. Let's pause here and think about what it means to observe the early universe. The universe began approximately 13.8 billion years ago in an event we call the Big Bang. In the first fractions of a second, it was unimaginably hot and dense. There were no atoms, no stars, no galaxies, just a roiling soup of fundamental particles and energy, expanding and cooling rapidly. As the universe expanded, it cooled. Within a few minutes, protons and neutrons could combine to form the nuclei of the lightest elements: hydrogen, helium, and trace amounts of lithium. But it was still too hot for electrons to join these nuclei and form complete atoms. The universe was opaque, filled with a fog of free electrons that scattered light in every direction. About 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with nuclei, atoms formed, the fog cleared. For the first time, light could travel freely through space. This moment is called recombination, and the light released at that moment is still traveling through the universe today. We can detect it as the cosmic microwave background radiation, a faint glow of ancient light coming from every direction in the sky, now stretched and cooled by the expansion of the universe to microwave wavelengths. But after recombination came a period astronomers call the Dark Ages. There were no stars yet, no galaxies, just clouds of neutral hydrogen gas slowly clumping together under the influence of gravity, pulled into dense regions by the invisible scaffolding of dark matter. Gradually, over tens or hundreds of millions of years, these gas clouds became dense enough to ignite. The first stars were born. These weren't stars like our sun. They were monsters, possibly hundreds of times more massive than the sun, burning fiercely and dying young. When they died in supernova explosions, they seeded the universe with the first heavy elements, and likely left behind the first black holes. The light from these first stars began to ionize the hydrogen gas around them, carving out bubbles of clear space. This period is called reionization, and it represents the universe waking up, transitioning from darkness to light. The first galaxies formed during this era. They were small, irregular, chaotic. Over billions of years, these proto-galaxies merged and grew, forming the grand spirals and ellipticals we see today. When we look at the most distant galaxies in the James Webb Space Telescope's images, we're seeing this process happening. We're watching the universe's childhood. And it's messier, stranger, and more wonderful than anyone predicted.
Not all galaxies are peaceful. Some are violent, chaotic. Some harbor monsters at their cores that pour out energy on scales that dwarf anything we see in our own Milky Way. Let me tell you about quasars. In the 1950s and 60s, astronomers using radio telescopes began detecting powerful sources of radio waves coming from deep space. When they turned optical telescopes toward these sources, they often found what looked like faint blue stars. But the spectra of these stars were bizarre, emission lines that didn't match any known element. It took years to figure out what was happening. Those emission lines were from known elements, hydrogen, oxygen, and others, but they were red-shifted so much that they appeared at completely different wavelengths. These objects weren't stars at all. They were incredibly distant, incredibly luminous galaxies. They're called quasars, short for quasi-stellar radio sources, and they're among the most energetic phenomena in the universe. A typical quasar can outshine an entire galaxy of 100 billion stars. All that light comes from a region smaller than our solar system. How is that possible? The answer lies at the center. A supermassive black hole, millions or billions of times the mass of the sun, actively feeding on surrounding gas and stars. Matter falling toward a black hole doesn't just disappear quietly. It spirals inward, forming an accretion disk, a swirling vortex of superheated material. Friction in the disk heats the gas to millions of degrees, causing it to radiate across the electromagnetic spectrum. Some of this material doesn't fall into the black hole, but is instead ejected in powerful jets that shoot out perpendicular to the disk at nearly the speed of light. These jets can extend for hundreds of thousands of light years, drilling through intergalactic space, lighting up vast clouds of gas with their energy. Quasars are so bright that they can be seen across billions of light years. In fact, the most distant quasars we've observed are so far away that we're seeing them as they were less than a billion years after the Big Bang. Somehow, supermassive black holes formed very early in the universe's history. How they grew so large so quickly is one of the great mysteries of modern astrophysics. But here's something remarkable. Quasars are rare in the nearby universe. Most of the quasars we see are billions of light years away, meaning we're seeing them as they were billions of years ago.
In the present-day universe, most supermassive black holes have run out of nearby fuel. They've consumed the gas around them. They've become quiescent, sleeping giants. Our own Milky Way has a supermassive black hole at its center, but it's mostly inactive. It occasionally snacks on a passing gas cloud or an unlucky star, causing a brief flare of radiation, but it's nothing like the roaring quasars of the early universe. The implication is clear. Galaxies go through active phases and quiet phases. There are times when the central black hole is feeding voraciously, and the galaxy is brilliant and violent. And there are times, like now in our galaxy, when the black hole slumbers and the galaxy is relatively calm. Let's talk about active galactic nuclei, or AGN. This is the general term for galaxies with actively feeding supermassive black holes at their centers. Quasars are one type of AGN, but there are others. Seyfert galaxies are spiral galaxies with bright, active cores. They're less luminous than quasars, but still much brighter than normal galaxies. Often you can see the spiral structure of the galaxy surrounding the brilliant point of light at the center. Blazars are AGN where one of the jets happens to be pointed directly at Earth. Because we're looking straight down the barrel of the jet, so to speak, the light is Doppler boosted and appears extraordinarily bright. Blazars can vary in brightness dramatically over hours or days as the jet shifts and pulses. Radio galaxies are usually giant elliptical galaxies with enormous radio-emitting lobes extending to either side, fed by the jets from the central black hole. These lobes can span millions of light years, larger than most galaxies themselves. All of these phenomena are powered by the same mechanism: matter falling into a supermassive black hole and releasing tremendous energy in the process. It's a cosmic furnace, turning mass into light with an efficiency that far exceeds anything we can achieve with our technology. And it reminds us that black holes, often thought of as cosmic vacuum cleaners that suck in everything around them, are also among the brightest objects in the universe. They don't just consume, they illuminate. Now let's talk about something even more dramatic: galaxy collisions. I mentioned earlier that when the Milky Way and Andromeda collide in a few billion years, individual stars will rarely hit each other, but that doesn't mean collisions are gentle events. The gravitational interactions between two galaxies can be catastrophic. When galaxies collide, several things happen. First, the gas clouds within the galaxies collide and compress. Unlike stars, gas clouds do hit each other. The compression triggers intense bursts of star formation. Thousands or millions of new stars are born in a brief frenzy of creation. These regions glow brilliantly, lighting up the colliding galaxies in ultraviolet and visible light. Second, the tidal forces, the differences in gravitational pull across each galaxy, can tear stars away from their home galaxies, creating long streamers and tails of stars extending into intergalactic space. Some colliding galaxies look like cosmic dancers, their spiral arms stretched into elegant ribbons by their mutual interaction. Third, the supermassive black holes at the centers of the galaxies may eventually merge. As the galaxies spiral together, losing energy to gravitational radiation, the black holes draw closer and closer. Eventually, they merge into a single, larger black hole. This merger releases a pulse of gravitational waves, ripples in the fabric of space-time itself, traveling outward at the speed of light. We've detected gravitational waves from merging black holes using instruments like LIGO and Virgo, although so far only from stellar mass black holes, not the supermassive ones at galaxy centers. But in the coming decades, space-based detectors will be able to detect the gravitational waves from merging supermassive black holes, allowing us to hear galaxy collisions happening billions of light years away. Some of the most beautiful objects in the night sky are colliding galaxies. The antennae galaxies, about 70 million light years away, are two spirals in the process of merging, their tidal tails extending like the antennae of an insect. The mice galaxies, so named for their long tails, are another pair caught in a gravitational dance. The whirlpool galaxy, which Lord Rosse first saw as a spiral, is actually interacting with a smaller companion galaxy, NGC 5155, whose gravity is enhancing the spiral structure. These collisions can take hundreds of millions of years to play out. They're slow-motion catastrophes, cosmic ballets performed over timescales that dwarf human history. But by observing many different colliding galaxies at various stages, astronomers can piece together the sequence of events and understand what will happen when our galaxy collides with Andromeda. It's both terrifying and beautiful to think about, terrifying in its scale and violence, beautiful in its inevitability and the new structures that will emerge from the chaos. Let me tell you about one more type of extraordinary galaxy, starburst galaxies. These are galaxies undergoing an episode of intense star formation, producing new stars at rates hundreds or thousands of times faster than the Milky Way. Often this is triggered by a collision or close encounter with another galaxy, which compresses the gas and triggers widespread starbirth. In a starburst galaxy, the central regions can be so crowded with newly forming stars that they're hidden behind thick clouds of dust. But the dust doesn't just block light, it absorbs it and re-radiates it at longer wavelengths, particularly in the infrared. So starburst galaxies are incredibly bright in infrared light, even if they appear relatively dim in visible light. The most extreme starburst galaxies are called ultraluminous infrared galaxies, or OLRIGs. These are usually the result of major galaxy mergers. All the gas from both galaxies is being funneled into the center, where it collapses into stars at a prodigious rate. An ORIG might produce hundreds or even thousands of solar masses of new stars every year. To put that in perspective, the Milky Way produces about one solar mass of new stars per year. But starburst phases can't last long. The gas gets used up quickly, massive stars are born, live briefly, and die in supernova explosions. These explosions heat up the remaining gas and can even blow it out of the galaxy entirely, creating a galactic wind that quenches further star formation. What's left afterward is often a red and dead elliptical galaxy, a population of old stars with little gas left to form new generations. The galaxy has burned bright and fast, exhausting its fuel. It's a reminder that galaxies, like stars, have life cycles. They're born, they grow, they go through active and quiet phases, and eventually they age into quiescence.
Now let's zoom out even further. Let's leave individual galaxies behind and look at the largest structures in the universe. Galaxies are not distributed randomly through space. They're organized into a vast, intricate pattern called the cosmic web. If you could see all the galaxies in the universe at once from an impossible vantage point outside it all, you'd see that they're arranged in filaments, long, thin structures where galaxies are strung together like beads on a necklace. These filaments branch and connect, forming a web-like pattern. Between the filaments are enormous voids, vast regions hundreds of millions of light years across, where very few galaxies exist. The cosmic web is the largest known structure in the universe. It's shaped by the distribution of dark matter, which forms the invisible scaffolding on which visible matter accumulates. Dark matter clumped together first, shortly after the Big Bang, and ordinary matter, gas that would become stars and galaxies, fell into the gravitational wells created by the dark matter. Over billions of years, this process created the structure we see today, dense regions where galaxies cluster together, connected by filaments, separated by empty voids. Let's zoom in on a specific part of this structure, a galaxy cluster. Galaxy clusters are the largest gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies all orbiting a common center of mass. The Coma cluster, for example, contains over 1,000 identified galaxies. The Virgo cluster, our nearest major cluster, contains about 1,300 galaxies and is about 54 million light-years away. In the centers of these clusters, the galaxies are so densely packed that collisions and near misses are common. Many of the galaxies and cluster cores are ellipticals, perhaps the result of all those collisions, which disrupt spiral structure and merge galaxies into smooth, featureless ellipsoids. But galaxies are only a small part of a galaxy cluster's mass. There's also hot gas, hydrogen and helium, heated to tens of millions of degrees by the gravitational energy of the cluster. This gas fills the space between galaxies and emits X-rays that we can detect with space-based X-ray telescopes. In fact, there's often more mass in this hot gas than in all the stars and all the galaxies in the cluster. And then, of course, there's dark matter. Dark matter makes up about 85% of a cluster's mass. We can map its distribution by observing how the cluster's gravity bends light from even more distant galaxies behind it, a phenomenon called gravitational lensing. Gravitational lensing is one of the most beautiful proofs of Einstein's general theory of relativity. Einstein showed that mass warps spacetime, and light traveling through warped spacetime follows curved paths. When a massive object like a galaxy cluster lies between us and a more distant galaxy, the cluster's gravity bends the light from the distant galaxy, distorting its image. Sometimes this creates multiple images of the same background galaxy. Sometimes it stretches the background galaxy into long arcs or even complete rings called Einstein rings. By analyzing these distortions, astronomers can map the distribution of mass in the cluster, including the dark matter we can't see directly. Some of the most striking Hubble images show galaxy clusters acting as gravitational lenses with dozens of distorted, stretched background galaxies visible around the cluster core. It's like looking through a cosmic funhouse mirror, but the distortions tell us profound truths about the universe's structure. Between the filaments and clusters lie the voids. These are the empty spaces, the cosmic deserts where few galaxies reside. The largest known void is the Boötes void, discovered in 1981. It's roughly 330 million light-years in diameter. In a region of space where you'd expect to find about 2,000 galaxies, based on the average density of the universe, the Boötes void contains only about 60. It's a region of profound emptiness. Standing in the middle of a void, if such a thing were possible, you would see very few galaxies in any direction. The night sky would be almost completely black. No Milky Way band, no nearby galaxies visible to the naked eye, just darkness with perhaps a handful of faint smudges visible through a telescope, all of them on the distant walls of the void. It would be perhaps the loneliest place in the universe. But voids aren't completely empty. There are small galaxies and dwarf galaxies scattered within them, and the voids are growing. The expansion of the universe means that the filaments are slowly being pulled apart, and the voids between them are expanding. In the far, far future, if the universe's expansion continues to accelerate, driven by the mysterious dark energy we'll talk about shortly, the voids will grow even larger, and the clusters will become more isolated from one another. Now, let's talk about the force that's shaping the universe's future: dark energy. In the late 1990s, two teams of astronomers were studying distant supernovae, using them as standard candles to measure the expansion rate of the universe. They expected to find that the expansion was slowing down, decelerated by the gravitational pull of all the matter in the universe. Instead, they found the opposite. The expansion is accelerating. This was shocking. It meant that there's some kind of energy permeating space itself, a repulsive force, pushing galaxies apart. This energy has been dubbed dark energy, and it makes up about 68% of the total energy content of the universe. We don't know what dark energy is. We don't know where it comes from. We can measure its effects. We can see that the universe's expansion is speeding up, but we have no fundamental explanation for why this energy exists. One possibility is that it's a property of space itself, a cosmological constant, as Einstein once proposed and later rejected, calling it his greatest blunder. Another possibility is that it's a dynamic field that changes over time. We simply don't know. What we do know is that dark energy is winning. While gravity pulls matter together into galaxies and clusters, dark energy is pushing the large-scale structure of the universe apart.
In the future, galaxy clusters will become islands separated by ever-growing voids. The cosmic web will stretch and thin. Eventually, galaxies outside our local group, the collection of galaxies including the Milky Way, Andromeda, and several smaller companions, will recede beyond our cosmic horizon, their light stretched to such long wavelengths that it becomes undetectable. In the far, far future, trillions of years from now, an observer in our merged Milkomeda galaxy will look out at a night sky that appears completely empty. No other galaxies, no evidence that the universe is anything more than a single island of stars surrounded by infinite darkness. Unless, of course, that observer understands the history. Unless they have records passed down from generation to generation of a time when the universe was younger and more crowded, when the night sky was rich with galaxies, when he could see our cosmic neighbors and study the grand architecture of creation. This is why we study galaxies now. This is why we photograph them, measure them, analyze them. We're documenting a universe that won't last forever in its current form. We're bearing witness to this particular chapter of cosmic history. Let's bring this back to something more intimate. Let's talk about life. When we look at a galaxy, a swirling mass of hundreds of billions of stars, we're not just looking at stars. We're looking at potential homes, planets, worlds, places where, perhaps, life has emerged. Our own existence proves that galaxies can harbor life. We're here, aren't we? We evolved on a planet orbiting a star in a spiral arm of the Milky Way. So the question isn't whether galaxies can support life, it's how common life is. Are we alone in our galaxy? Are there other civilizations out there looking up at their own night skies, wondering the same things we're wondering? Let's think about what a galaxy needs to support life as we know it. First, it needs stars. Not just any stars, but stable stars that will burn steadily for billions of years, giving any planets around them time for life to evolve. Massive stars burn too hot and die too quickly. The smallest stars burn dimly and might not provide enough energy. But mid-sized stars, like our Sun, seem just right. Second, the galaxy needs heavy elements. Carbon, oxygen, nitrogen, phosphorus, iron. These elements are created in the cores of stars and scattered into space when those stars die. The first generation of stars, formed from the pure hydrogen and helium of the Big Bang, couldn't support life because they had no heavy elements. But later generations, enriched with the ashes of earlier stars, could. Our Sun is a third-generation star. It formed from a cloud that already contained the heavy elements needed to make rocky planets, and eventually living organisms. Third, the location within a galaxy matters. Too close to the galactic center, and you're exposed to intense radiation from the supermassive black hole and high-energy events like supernovae, which are more common in the densely packed core. Too far out, and there might not be enough heavy elements to form rocky planets. There's a concept called the galactic habitable zone, a region of a galaxy where conditions are favorable for life. For the Milky Way, this zone is thought to be a ring at a certain distance from the center, where there's enough heavy elements, but not too much radiation. Our solar system lies in this habitable zone. We're in the Orion Arm, a minor spiral arm about 26,000 light-years from the galactic center. It's a relatively quiet neighborhood. Supernovae are rare here. The radiation environment is mild. But how many other solar systems are in similar locations? How many planets are orbiting sun-like stars in galactic habitable zones? We're only beginning to answer these questions thanks to missions like Kepler and TESS, which have discovered thousands of exoplanets, planets orbiting stars other than our own. We now know that planets are common. Most stars have planets. Many of those planets are rocky and roughly Earth-sized. Some orbit in the habitable zone around their stars, not too hot, not too cold, where liquid water could exist on the surface. If even a small fraction of these planets develop life, the Milky Way alone could contain millions or billions of living worlds. And the Milky Way is just one galaxy among hundreds of billions of galaxies. The potential for life in the universe is staggering. But there's a paradox. If life is common, if the galaxy is teeming with civilizations, then where are everyone? Why haven't we detected any signals from alien civilizations? Why haven't they visited us? This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked, "Where is everybody?" There are many possible answers. Maybe life is common, but intelligent, technological life is rare. Maybe civilizations arise, but destroy themselves before they can spread through the galaxy. Maybe interstellar travel is too difficult and civilizations stay confined to their home systems. Maybe they're out there, but they're so different from us that we wouldn't recognize their signals or their technology. Or maybe we're early. The universe is 13.8 billion years old, but it's going to last for trillions of years. The era of star formation is winding down, but it's not over. Maybe life is just beginning to emerge in galaxies across the universe. Maybe we're among the first. Or maybe, and this is a humbling thought, maybe advanced civilizations are out there, but they simply haven't noticed us yet. We're like ants on an anthill next to a busy highway. The cars roar past, but the ants have no concept of what they are, and the drivers don't notice the ants. We might be surrounded by galactic civilizations that are so advanced, operating on such different scales and time scales, that we're invisible to them, and they're incomprehensible to us. We don't know. And that not knowing is one of the most profound questions we face as a species. Since the 1960s, we've been conducting SETI, the search for extraterrestrial intelligence. We point radio telescopes at nearby stars, listening for signals that might indicate the presence of a technological civilization. We've listened to millions of star systems. So far, we've heard nothing conclusive. But the search continues, and it's expanding. We're now also looking for laser pulses, brief flashes of light that might be an alien civilization's way of signaling. We're analyzing the atmospheres of exoplanets, looking for biosignatures, chemicals like oxygen and methane that might indicate the presence of life. And we're thinking more carefully about what alien life might look like. Maybe it's not based on carbon and water. Maybe it uses different chemistry entirely. Maybe it exists in environments we consider hostile. The subsurface oceans of icy moons, the atmospheres of gas giants, the interiors of neutron stars, though that last one seems pretty unlikely. The universe is full of possibilities, and galaxies are the theaters in which the drama of life, in whatever form it takes, plays out. When you look at a picture of a distant galaxy, try to imagine what's happening there. Are there planets orbiting some of those stars? Are there oceans, forests, cities? Are there beings looking up at their sky, seeing our Milky Way as a faint smudge, wondering if anyone is out here? It's a beautiful thought, a lonely thought, perhaps, but also a hopeful one. Because if life exists elsewhere in the universe, then we're not alone. We're part of a community, even if we haven't met our neighbors yet. And even if we are alone, if we're the only life in the entire observable universe, that makes us precious. It means the universe has become aware of itself through us. It means that when we study galaxies, we're the universe studying itself. We're star stuff, contemplating star stuff. Either way, we matter.